Thanks. I'm Jesse Burns.
And I'm Peter Eckersley.
And we're from San Francisco. And this is a fun project we've been doing for about a year. It's thanks to EFF and the NLNet Foundation. And we've been looking at certificate authorities. And every time you see a certificate authority, you get this idea that someone's telling you what to do, there's some authority there, and people should be thinking about what the authorities are, what they're doing. And so we thought we needed to observe that, and we started an observatory for the SSLiverse.
So the basic observation here is that if you have cryptography, for instance, you want to use cryptography to protect the web. The web is a pretty important thing, and we think that HTTPS is the future of the web. So we want to use cryptography to protect the web. But cryptography is only ever as good as your ability to identify the other party that you're talking to. In the case of HTTPS, it's your ability to identify that the website you're going to and having an encrypted conversations with is really google.com and not some Russian website that's impersonating it. And in particular, HTTPS relies on certificates to do this. And the certificates are signed by these entities called certificate authorities, who give you a little piece of paper or a little file that says, yeah, this key over here, this public key, really belongs to google.com or mail.google.com or whatever the particular domain is, and your browser trusts some list of these. And we're afraid of certificate authorities for some specific reasons. Last year, there were 3 vulnerabilities that were directly or partially attributable to mistakes made by certificate authorities. In one case, it was that they were using MD5, which was known to be weak, and not randomizing their serial numbers, so people were able to predict a collision in the MD5 they would sign. Another vulnerability was arose because certificate authorities were willing to sign certificates that had /0s, 0 bytes inside the names of domains. And then it turned out that although the certificates could include the /0, browsers would parse that as an end of string and interpret the certificate incorrectly. And the last example was a certificate authority that was willing to give you a certificate if you could answer email from a large list of domains, of email addresses at a domain. So if you could answer email for webmaster@domain.com, root@domain.com, administrator@domain.com, then they would give you the certificate. And so someone demonstrated, well, here's a webmail system, and I got root at that, or administrator or whatever at that domain because it was a Windows system and they didn't protect root as a username. And so we have these problems. This year, there has been emerging evidence that intelligence agencies and spy technology companies are selling devices that will do SSL man-in-the-middle attacks. And their marketing material says, if you need to get rid of the certificate warning, just go and get a certificate authority to give you a certificate for the domain you're eavesdropping. So if that is actually happening, then that's a serious problem. And regardless of these specific incidents of potential problems with CAs, there's a structural problem, which is that when we have dozens or hundreds or thousands perhaps of CAs, and it only takes one to sign a malicious certificate, then your probability of having a successful attack goes up and up and up. And the probability that a determined adversary can find a CA somewhere that makes a mistake and breaks your system is just too high. And we're also afraid not only of the certificate authorities, but also of the certificates themselves. These objects use a file format that was defined in the 1980s by the ITU, which is the international organization where telecommunications companies form their standards. And this file format was designed before the web existed. And somehow they've managed to bolt the web onto this pre-existing standard. And that's evidence of the incredible flexibility and generality of X509, which is also a terrible flaw. This file format is incredibly ugly, and as I said, there are vulnerabilities that arise from its use, have arisen from its use regularly in the past. And I'm going to give you a metaphor for this. If you want to understand what's going on with these X509 certificates, think of a giant pile of pieces of paper stapled together. And the security of the encrypted web is based on a huge collection of these things. And the form that is in each of these files is not clearly defined. There's no standard answer for what fields will be present in the form and what will be in those fields. In fact, if you look around and compare them, they have different things all over the place. And so it's very hard to write software that is going to perform reliably when you don't know what kinds of input data it's going to be handed. So we set out to deal with this problem. And we thought about two approaches. One was, well, could we go and look at the browser and modify the way that browsers decide that google.com is really google.com? And indeed, there are some projects out there that are doing things like this, Perspectives and MonkeySphere and so forth. None of them are really widely used yet. Could we maybe build on top of those projects and get a more reliable way of having your browser know that the website is what it's supposed to be? And we decided that that was actually very hard to do correctly at this point. We don't have a clear enough idea of where we want to get to. So instead, the second option, let's study what's going on today. Let's get a data set of what the certificate authorities are signing and look inside and see what happens.
Yeah, one of the models that's not really used a lot on the web yet is TOFU, trust on first use. And if you think of your SSH client hooking up to your SSH server, no authority gave you permission. It just lets you know that it's the same server that it was last time. And if you installed the thing wrong, then or you were attacked at the very beginning of time, you're going to be in trouble. But that seems to be a pretty successful model. There's definitely lots of other things that we could think of that would be alternatives to this that might be more effective. So
a good point. That's a great point. The thing you need to understand, the reason that the SSH model works well for SSH, and perhaps better for SSH than it would for HTTPS, is that when you get that error message from SSH saying the keys on this server appear to have changed, you have a high probability of being able to find out whether they were supposed to have changed and why they had changed. You may be the sysadmin, in which case they shouldn't have changed unless you reinstalled the box. Or if you're not the sysadmin, you should know the sysadmin, and you can call her and say, hey, did you reinstall that server? Okay, I understand why the keys have changed. If you're trying to contact a website on the other side of the world, you don't necessarily know why or whether the keys are supposed to have changed. And so it is harder to do trust on first use for HTTPS. It doesn't mean that it's never going to be possible, but we should certainly think about that option. Anyway, in the meantime, we have this project, the EFF SSL Observatory. What we did is we scanned all of the public IPv4 space on port 443 and downloaded every single HTTPS certificate that's available on the public web. It took about 3 months. We used 3 computers. And we wrote a giant, a complicated set of scripts that we're going to be showing you some of for analyzing this data. Remember, what we're dealing with is data that looks like this. And so writing good code to handle that data is tricky. And then we presented some initial results at Defcon, and we're presenting some more now. So we're going to give you a brief overview of the things we said at Defcon, some new results because we rescanned, we went out and got a new copy of the data from December rather than May to June, which is our first data set. And then we're also going to focus on showing you guys how to use this data because we've published it. There's a BitTorrent file you can use to download the giant MySQL database with all of our stuff. But the problem with that is it's really complicated. Remember, it looks like this. And so most people who download that thing won't have any idea what to do about it or do with it. So we're going to try and show you some things you can do with it. And then hopefully people can go out and find new interesting things to learn from this data set. And lastly, we're going to conclude with a little bit of a proto-design for a decentralized version of this thing. Right? We scanned all of public IPv4 space from a data center in San Francisco. But we want to do this from everyone's computers because sophisticated attackers are never going to put their attack certificate on a public web server. They're only going to show it to the target. And so we need a decentralized version of this technology. So the size of what we found, if you look at IPv4, actually this is a slightly old number, but between 16 and 17 million IP addresses will answer a SYN packet on port 443. Of those, 11.3 million started an SSL handshake. If you look inside those, 4.3 million of the 11 million SSL handshakes are something that we thought a browser would consider a valid SSL certificate. You wouldn't get that cert warning in the browser. And then inside those 4.3 million handshakes, you've got 1.5 million distinct kind of leaf and entity certificates. And the reason that the last number is smaller than the previous one, of course, is that sometimes sites have multiple IP addresses with mirrored web servers.
Or the same cert gets repeated over and over again.
Right, the same certificate can be on multiple web servers.
One of the other little things about doing this right now is that we're still on IPv4, and when we move to IPv6, this isn't going to be an approach that we can try. Also, there's a new protocol, what is it? SNI, server name indication, where a client actually says who it expects to hear when it makes an HTTPS connection, and that's going to really mess up our ability to just sort of say, hey, who are you, and hope that the server honestly tells us all the certs it has. So this project is going to become a little bit more difficult to do in maybe a year or two. IE6 right now doesn't really support SNI, and so ironically we're able to, take advantage of that to still collect this data.
As Jesse just said, there's very little virtual hosting over HTTPS right now. There will be a lot more in a few years, and so this technique will work for the intervening time. So before I go to the next slide, forget what you saw if you saw the answer. How many of you think you have an idea of how many certificate authorities your browser trusts? Okay, a bunch of you, like 24 people in the room, have a guess. Now, how many of you think that number is more than 10? More than 50? More than 100? More than 200? More than 300? More than 400? More than 500? More than 600?
Come on.
People, more than 1,000. Anyone think more than 1,000? People who saw our talk at Defcon.
Yeah, okay.
So, this is how many certificate authorities browsers trust. Now, you get a very wrong answer if you go and look in the browser user interface for two reasons. If you look at Mozilla, you're missing out on the whole existence of subordinate or intermediate certificate authorities. So any one of the certificate authorities that Mozilla trusts can sign another certificate and give it to someone else, and they're now a certificate authority, and Mozilla will trust that. And so that accounts for a large fraction of these. The other portion is that with Windows, if you go and look at a modern version of Windows, it has a very short list of certificate authorities. But if you go to a website that's signed by someone else that's not in that list, IE pings Microsoft and says, should I trust this? And Microsoft says yes, and now you trust it. And I mean, that sounds utterly terrible. There was, in fact, a reason why they chose to do that. In engineering terms, it makes it easier to roll out new certificates in a predictable way. But even so, it makes life pretty hard if you want to be a systems administrator and go through the list and decide who you trust.
It's also a bit of a threat to certificate authorities that use weak keys, because to get in their list that they ship, you have to have good, strong keys. And so, if you've got some CA that's got a 1024-bit key, they're going to say, oh, well, everyone who uses your CA is going to have a little extra latency, and it's just going to kind of suck. And if, by the way, there's ever a break in an RSA 1024-bit key, we're going to pull you. So, it's a little bit of a stick.
There are benefits to doing this, but it means that list right now in Internet Explorer is kind of malicious.
Yeah, it takes a long time to figure them out, too, because you have to go and figure out where to download it from, and, anyway.
So, we made a map of these certificate authorities. Unfortunately, it's kind of too large to show on a PowerPoint slide. We can print it out if we have like an A3 or larger size printer. You can print it out so that this is legible at all, but mostly it's just so large and incomprehensible that you can't. So this over on the left here is the whole map. You can see how tiny it is. There's no way you guys are ever going to be able to read that. I've zoomed in on one little portion of this so that you can see kind of what it looks like. We've got an outdated version of this on our website. I'm going to put an updated version right after the talk. I'm going to go and put the full color, nice PDF version online. I should have done it before I came over here, but half an hour after the talk, you'll find this PDF for your own viewing pleasure. If you look inside it, it contains lists or maps of these certificate authorities. The key is a square is a root certificate authority that is trusted by both Mozilla and Firefox. I mean, it's Mozilla and IE. This is a root certificate authority that's only trusted by IE, the hexagon. So Deutsche Telekom only trusted by IE, Global Sign trusted by both. And then these ovals are subordinate certificate authorities. So these people got to be CAs because someone else went out and handed them a CA certificate. So you can see Deutsche Telekom gave Fraunhofer the right to be a certificate authority. And in fact, Deutsche Telekom, if you follow this arrow here in the map, Deutsche Telekom also gave an organization called Defcon the right to be a certificate authority. And as you can see in this map, Defcon handed a lot of subordinate certificate authority keys to other third kind of organizations in the chain. So actually, of the 650 organizations that are certificate authorities, about 230 of them are German universities and other institutions that got to be certificate authorities because Defcon gave them the right to do that. And so no one tells you this when you look at your browser and you try to see who it trusts. But all of this stuff is going on in the background. So some other noteworthy subordinate certificate authorities. You might not look in the list and see that you trust the Department of Homeland Security, but you do.
We found a total of one website on the internet that used that certificate. And had a little notice saying it was going away soon. But their cert doesn't expire for a long time.
There are US defense contractors?
Yeah, like Booz Allen Hamilton. They do some tricky stuff. I don't know if you want to trust them. One of the ones that's kind of fun is CNNIC. You might remember there was a big kerfuffle about putting these guys in the Firefox trust root. And it turns out that they've had a subordinate CA since 2007. So anything that was signed with their cert, all it had to do was present an intermediate cert, and poof, it would have already been accepted by Firefox. So there shouldn't have needed to be any debate over that root CA because we already trusted them and we just didn't know. So, although you can pull it out and it'll be harmless.
Etisalat is the majority state-owned telecommunications company in the United Arab Emirates. They created quite a scandal because about a year and a half ago now, they installed malware on 100,000 of their BlackBerry subscribers' devices. And they didn't use an SSL certificate to do that, but they did use signing keys from from the BlackBerry development API to sign their malware and say this is okay, it can have access to the trusted BlackBerry API portions. And then in the year after that, this company got back in the news because the UAE government got very angry with BlackBerry for having told people to uninstall this patch and issued like a fix for the malware. And so for a brief period of time, there was a threat to disconnect all the BlackBerries in the UAE over this secure crypto stuff. So given that this company has demonstrated an institutional hostility to the existence and use of secure cryptography, perhaps we should wonder whether in fact every single browser on the planet should trust their CA certificate.
Nah.
And lastly, the Gemini Observatory. We're an observatory too. And in fact, we're a much more SSL-focused observatory, so perhaps we hope that at the end of this talk we can be a certificate authority as well. We have exposure to a lot of countries' jurisdictions. So here are the list of countries, if you believe the country field in the certificates, that have certificate authorities. I mean, if you believe them, who knows where these people really are. So theoretically, the law of any of these countries can be used to obtain a malicious certificate to attack somebody somewhere. Latvia, Lithuania, the United Arab Emirates, as I said, Tunisia, Hong Kong, Macau.
Zimbabwe. Or is that Zaire?
South Africa.
Oh, South Africa. Oh.
Anyway, the point is not that any one of these countries is untrustworthy, just you're exposed to every single government in the world, or at least a third of the governments in the world, when you play this game. So, we also saw some vulnerabilities. Probably the largest one that we saw, I'm sorry, this is still the Debian weak SSL keys bug. It's still out there. We saw 30,000 servers that use a certificate for a completely broken SSL private key. Of those 30,000, fortunately, only 500 of them were valid in browsers. But the things that we saw that were valid included a few pretty important websites. So the Belgian government's diplomatic arm was using one of these. Yandex, which is the largest webmail, it's like the Russian Yahoo, was using a broken private key. And the University of Chicago Law School's webmail system was using one. And some pretty powerful people have accounts on that webmail system. These are all fixed or expired, so we're not telling you guys that you can now go and break into these systems. And we've tried to email all the people who had these broken keys, but it's actually very hard to find a reliable way to email 500 or 30,000 people's accounts. The best you can do really is the whois entries. The certificate authorities that should be revoking these things are extremely hard to contact. In general, certificate authorities, there's no way you can go in and look at a certificate and say, how do I email these people and tell them they've signed something vulnerable? Unless you know them in person, you can't do it. We saw all sorts of other wackiness. There was one Quo Vadis certificate that if you looked inside to see if the thing they'd signed was itself a certificate authority, one of the fields said no, and then the key usage field that addresses the same question said yes, you can sign certificates with this. Just one. There was one in the whole, on the whole internet. There are a lot of certificates for domains like localhost and mail, and 127.0.0.1, or even public IP addresses. Actually, the public IP addresses are perhaps more defensible than the other things, where it's just completely meaningless to know that you have a secure connection to mail when 5,000 other people have a certificate for mail as well.
And you get a discount when you buy them because they don't have to actually check anything, right? Because everyone's mail. That's true. Unqualified names, this is a really dubious idea that you could ever have an unqualified name, right? I mean, if a name isn't qualified, what does it mean to have exclusive ownership of it? It's nothing, right? So the same with IP addresses that are RFC 1918, like the internal ones, 192.168 or 10 space. You could maybe make an argument about IP addresses, but unless you're a member of NANOG or something, probably IP addresses aren't something that you really relate to, right? So it might be.
And we're going to talk more about the last point, violations of the extended validation rules later, because there are a lot of those. And as I said, we've published the data. It's EFF.org/observatory. You can BitTorrent it. And play with it. It's a large download. The compressed blob of just the database or just the raw input data, either of those is about 4 gigabytes, maybe 5, I can't remember exactly. And then once you untar it and feed it into MySQL, expect at least a 12 gigabyte table for one thing and maybe some other large tables lying around as well.
Don't untar the results files unless you have a lot of disk space and a file system that has a lot of inodes.
Oh yeah, don't use, make sure, check your file system. Like it doesn't work, X4 or X3 or X2 are bad ideas. You need to format with something that has an unbounded number of inodes.
Yeah, JFS is what we used, mostly.
Works okay. Expect it to take about 10 hours to just decompress and feed it into MySQL on a fairly fast machine. Obviously, if you have something really fancy, maybe you'll get a faster result, and your average PC might be slower. And there are lots of weird things still in this dataset. We're hoping to release a new, cleaner version. The problem is it takes so long to do anything to the data, to reformat it or rename things, that it's actually like a month-long process to do a rebuild of everything from scratch and give you guys a nice, clean release. So we'll do that, but it might be a month before we do. The schema is fairly baroque. Partly, this is X509's fault. It's just this file format is crazy, and so if we tell you what's in the file format, the results are crazy. And partly because there are only 2.5 of us working on this, so Jesse and I, we got some help from Chris Palmer as well, and just we haven't had time to go through and do a completely clean, sane version of everything. But we'll show you how to use what we've got so far. These are the basic steps. This is mostly for the benefit of people looking at the slides later. Follow those steps to get the data. You have this schema. There are a couple of big, very important tables, the valid certs table and the all certs table. So this is every single certificate we saw. These are just the ones that were valid in a browser. They have 2 indexes. One is just an arbitrary serial number, cert ID, that will change between releases of the database. The other is a fingerprint, a SHA-1, which is currently unique, but will change once someone breaks SHA-1 and you've got attacks against it.
That'll be fun.
We have these names and a names. So this is all the names that, like domain names that map to valid certs. It's domain names plus other weird arbitrary names, because in X509, there's no domain name field. Who would have thought? They didn't have like the web. They wouldn't have thought you'd need a domain name field. So they have this common name field. Some certificates use that for a domain name. Other people put an organizational name in there, or an email address, or whatever else. It can be anything. And so you get all this wackiness. And then there's a subject alternative name field, which also contains more names. So we've munged all of that stuff together into these nice handy names fields for you. And then we have this cert scene table, which gives you a mapping between a time and an IP address that we saw something and the fingerprint that we saw there. So some simple examples. Suppose we want to know how many valid certs there are out there that have really like flimsy key lengths. You can write a query like this. It's a simple group by MySQL query. Select the number of bits in the key and the number of things that match that from the valid certs. And you see there are 3 certificates on the web that use a 511-bit key, about 4,000 that use 512. And then really, there are not a few stragglers in between here, and then really most certificates use at least 1024, which is going to be vulnerable soon, but perhaps not vulnerable yet.
NIST says you're allowed to use it till New Year's.
That's, what, 2 days?
Yeah, well, it's better than nothing.
You might also be interested, if you followed the MD5 collision attack against all of this stuff, in the question of, did the certificate authorities learn that they need to stop using MD5? And the answer actually is yes, largely. Not completely, just almost yes. So if you say, pick the signature algorithm and then the number of things certificates that use that from the valid certs, where it was issued this year. So we're just like, we know that they were vulnerable in the past. As of this year, have they learned? And so you can do this query, and you see, oh, there are 3 certificates in 2010 that were signed with MD5. And then you can go and do a query to find out who signed them. So select the issuers of these certificates. And there you go. There are the 2 certificate authorities that don't yet know that MD5 is collidable. And actually, this isn't really a vulnerability, because these 2 certificate authorities, the French Ministry of Justice and Anthem, which is a US health insurance company, hopefully neither of those certificate authorities will sign something that you guys send to them. Hopefully they just sign internal certificates and not anything. If they sign stuff that you guys send to them, then they're vulnerable. You can send them a weird thing that turns into your own private secret CA. Hopefully they don't do that. there are a lot of caveats with this data set, things that you can trip over. Here's just one example. If you look at, there's an IP field in the valid certs and all certs tables. It shouldn't really be there, but it's there for historical reasons. If you do a count distinct IP from there, you'll get a number that's too low because we've made those valid certs and all certs tables unique. If you want to know how many IP addresses had a certificate, then you need to look at this scene table. Validity is a really complicated business. There are two columns in our tables that relate to validity. And they're just the raw output, basically, of this OpenSSL verify command. By the way, you guys would probably think that it's easy to use OpenSSL to check if a certificate is valid, right? I mean, not easy, but you'd read the man page and you'd work it out. It took us probably 2 hours to work out what the trusted and untrusted arguments to the OpenSSL verify command do. It turns out the way you're supposed to use them is like this. If you've got a chain of certificates that's handed to you by some web server, so the certificate at the end of the chain is the thing for the web server, and then the rest of the chain is the list of intermediate certificate authorities that are supposed to go back to some root you trust. You stick the chain, all the bits of the chain, in this untrusted flag. You stick your store of root certificates in this bit, and then you hand it the cert as the last argument. And when you look at these columns, they have contents that are kind of like this. So if it's valid, it'll say yes. But it'll say self-signed OK if it's a self-signed certificate. So it's not yes, no. And then when there are errors, it'll say things like self-signed and all this explanation, or no and all this explanation. So if you look at the data set and you do some queries against it, you see stuff like, how many of the valid certificates had yes for Mozilla? 1.3 million. How many of the valid certificates did not have yes for Mozilla? That's the right way to say how many were valid in some case but not for basic Mozilla. And then Jesse's in the way, 170,000, and there were 213,000 that were valid for something but not for IE. Now, it's more complicated than this. So, in particular, both Firefox and IE, if they see an intermediate certificate authority, they cache it. They cache that intermediate certificate. And so that means that henceforth, whether or not a website is valid will depend on what you've cached. And so there's no way that OpenSSL can know what you've cached and look at a certificate and say, or a chain of certificates and say, yes, this is valid in Firefox, or yes, this is valid in IE, because you need to know what websites the user went to first. So we introduced this concept of transvalidity just in our data set. This is a certificate that's valid, but only if the browser had been to the right websites first.
Or alternatively, if the person who presented this certificate were to present other intermediate CA certs that we found already signed on other sites.
Right, but they failed to do that. So if you went with a clean profile, you'd get the certificate warning, but if you browsed around for a while, you wouldn't get the certificate warning. So we catch all, or perhaps almost all of these and mark them as transvalid. The way we do that, hang on to your seats. It's with this little script called transvalid.py. You can look at it in our code that's going to be online after the talk. But the core query, this is the magic you can get into with this SQL database. The core query just goes in and says, look, find me invalid, well, actually certs1 is the raw input table. Join it against the valid things, where the valid thing we're looking for is a potential intermediate CA that might have signed us. And the criteria for that are, first of all, the issuer and the subject need to match. That's how X509 works. Whoever issued, the subject of the person who issued you is your issuer field. And then if there are also these key ID things, and if they're present, they have to match. That's what these OR fields are for. And then where the error message we got from OpenSSL was failure to find the intermediate thing. So we checked for the error message in the existing attempts to verify, and if it was unable to get local issuer, then we pluck it out. And then what we do is we go back, we rerun OpenSSL. having added all of the valid things we saw on other web servers that look like they'd be the missing link in your chain. And then we estimate trans validity, and we found that 97,000, so about 100,000 certificates out on the web are valid, but only if you've been to the right websites first. So all of this is just in the table. So partly what I'm doing here is if you need to work with this data, you'll have no idea what trans valid means until you've read these slides.
Yeah, it's not really obvious.
And then there's this little simple valid variable, a Boolean valid variable, that's just, if any of these three cases, MOS valid, MS valid, or trans valid are true, then we just mark the certificate as valid.
Don't you have to repeat this process?
We did it just one step, on the theory that almost any intermediate certificate authority that's going to be used in one place is going to have been used correctly somewhere else. And so, yes, theoretically, you could have something that, like, where you could puzzle together a chain of intermediate certificates from different places, and I just think that in practice it's very unlikely that more than 0 or 1 or 2.
It'd be great to try. Actually, yeah, it's a great example of something that would take a long time to try, and if you found something, that'd be sweet.
Yeah, absolutely. You could totally, if you have a week of computer time, just try it.
Or a lot of RAM.
So more examples of what you can do with this data. This is a question that we asked in the course of building the graph that we showed you before, the big complicated graph. How do you find out which certificate authorities created the most of these other subordinate certificate authorities? So we have this little Python script, subordinate tracking, and what it does, it's got a loop in there. It runs for each root certificate. It says, so find us the things that were issued by this root certificate that are also certificate authorities, and where all the criteria for being a correct child of that certificate authority match. So either these key IDs are null or they're equal to each other. We do this recursively. So we find all the subordinate CAs that this root signed, and then all the subordinates signed by those, and those, and those, etc. And we get a number. We also counted the number of leaves. It's basically the same code. And the results, this is the top 8 list of the most proliferate certificate authorities. So, as I mentioned before, Deutsche Telekom is at the top of this, and the reason is not because Deutsche Telekom signed lots and lots of certificate authorities, but because they gave a certificate authority key to DFN Verein, and then DFN Verein gave it to everyone. So they're at the top. Huge numbers of certificate authorities, lots of weak points in the planet's web encryption infrastructure for a very small number of web servers. Like, really, it's not clear that you're getting a net benefit trusting all of this for 4,000 hosts. Of course, it's just IE. Firefox doesn't trust this top one. I think all the rest are trusted by Firefox. So this is CyberTrust. Oh, it is? Deutsche Telekom? That's a mistake. We should actually get them to take it out. We've never won one of those threads, ever.
Oh no, that's not true. Well, we got some certificates revoked.
None of those threads have ever resulted in a certificate authority being removed from Firefox.
Right. Or marked non-ED.
And then, of course, you can see the trade-off. So, I mean, AdTrust and VeriSign are doing lots of certification work. And so some number of subordinate CAs make sense for these organizations. But you get these other cases. I don't even know what this is. It's a French something. And it has 24 subordinate certificate authorities. So let's talk about extended validation.
All right, extended validation. So one of the little problems with SSL is that certificate authorities decided that domain validated would be what they did, and you know, that race to the bottom kind of culminated in you just get an email and that's proof that you're who you said you were. That's not a brilliant plan. So the big idea of extended validation would be that certs would become reliable again. And you can see their guidelines up on the website here. They've got a lot of strict rules now, like owners have to exclusively own domains. This is the crazy idea that maybe it should be actually you, right? So localhost shouldn't show up in here. unqualified names, right? Makes sense that those aren't exclusive, or RFC 1918 addresses shouldn't show up in here. They should use relatively strong keys. So the rule is that they can't have anything shorter than 2048-bit RSA as of the end of this year. So right now, all of those 1024-bit RSA keys are about to expire on midnight. They also should have identifiable owners, so that you should be able to read the actual properties and figure out who it is that signed them. And then there's also auditing requirements, so you can have some idea who it is that, or someone's checking this.
So probably a quick aside to throw in here. Extended validation has a user interface component to it. So on the server side, on the back end, you have these guarantees of graded security. The idea is that the user will have a different experience, and the different experience is the green address bar, the green URL bar.
You're in a happy place now.
Rather than the blue or some other color that you get for other websites.
So fortunately, the Chromium browser has some easy-to-read source code that explains how this validation happens.
There's no spec for it.
And it's a little bit messy. So every someone reverse engineered IE and wrote a spec that they found and then put some comments about. And anyway, these OIDs all correspond to different certificate authorities, and some magic happens. And if you have one of these OIDs in your certs and you're signed with the right root at the end of the chain, then you're going to be good. So we took this and we made an ugly where clause for our database here. And that lets us dig for stuff. So it's kind of a cute thing, and we found a bunch of stuff. So first of all, just before we even start looking at the information, we know a priori from other talks done by other people that browsers use the same origin security policy, and it's not super compatible with extended validation, right? It's not a different scheme. Same origin policy says if you're the same scheme, you can reach into the DOM. So if you've got like an iframe that for some reason is using a non-EV certificate, it can reach into the EV part and pull the data out and read the cookies and all that fun stuff. So not necessarily like the best thing for the browser, which is where you get the UI candy he was talking about, but that's not the big deal. Another problem with it is that it's really the same CAs that are doing this, but hopefully now they're going to be all accountable, and they're going to carefully audit everything, and we won't find any. This is going to be a slow, short presentation. And then they're supposed to have certificate policy statements, and we took a look at these, and it's kind of cute because most of them are served over HTTPS, as you might guess, because they're, the EV certificate policy statements for HTTPS, but there's actually 7,239 of them that we found that were served over HTTP, which I just thought was cute because it was a gander goose sort of thing. But what we found was 34,000 EV certs and 38 different issuers. Not all of these are really used, but that's okay, actually. One of the main reasons you find a CA that isn't in use is that it's using a really strong key, and they just want to get it out there widely before they migrate over to it. So you see something with only one signed cert, and it's still legit. So here are the problems that we found. The summary of it is we found RFC 1918 addresses, unqualified names, even the name localhost in an EV cert, weak keys, and long expirations. And that's the fun part, but I want to just show you how to use the data to find them. So, so the EV crypto policy violations. So we found 13 of these issuers have been used to sign 127 different valid certs that had expirations after the end of this year and used the weak key. So the spec says, this about that, so that's no good, not allowed to do that. Another really obvious thing about EV certs is that they're not allowed to have wildcards, right? You can't have star domains. And, CyberTrust spec'd a couple of these guys. Oops. Sorry. And then we also found these unqualified names floating around in there, including like webmail, so just webmail. We also found localhost, and that was good because actually right after Defcon, that one got revoked when we mentioned, when some Firefox guys came and asked us what some funny EV certs were that we saw, and we told them about some good things, and there was a little audit. And some of these are by major class 3 extended validation CAs, like VeriSign. So one of the other big no-nos is you don't want to sign these internal IP addresses, right? They're private, and I've got one, and you've got one, and so do everyone else. So it would be really meaningless to have a certificate like this. So we reported one of these to some people that asked us about it at Mozilla, and they went and told GlobalSign about it. And GlobalSign said, oh, they changed their policy way back in 2009, and they did an audit, and they must have just missed that one. And so we did another look after we collected more data, and we just noticed another one. So, oops. Here's an example of it. This is a website from the, what is this, the Iowa Credit Union group. I like it because it has the McAfee Secure badge. So, McAfee Secure. So here we go. There's that green bar. That's what you're getting with the EV. And here's their certificate. And you can see in the certificate subject alt names some IP addresses here in your 192 space. So, oops. But we also found a 512-bit EV cert. These guys at Thomas Betts Corporation in Memphis, Tennessee, managed to convince a CA to give them a 512-bit cert in September of this year, and it doesn't expire until 2012, which I think is after the end of the year. Yeah, so that would be like after the 1024 bits are supposed to be no good. So here's how you find a 512-bit EV cert. Query's a little nasty. But the idea here is we grab the cert ID and the RSA modulus and the name from our valid certs table, and we just naturally join it against the names table. And we say, oh, we only want ones with this 512-bit modulus. And then this is that huge where clause I showed you before for the finding SSL or EV certs, and it pops right up.
And there it is.
And there's all the major browsers viewing it. So yeah, we've got IE in the back with its nice little green bar that mentions the CA. And then we've got, there's that Chrome in the middle there, and Firefox. So all of them give you a nice EV experience for this 512-bit. Okay.
So, things we're going to do. Right after this talk, I'm going to go and put up an improved version of the graph and our up-to-date code, including some of these things that we demoed in this talk. But the bigger piece of further work. Sorry, I guess in between 1 and 2, also in the next month or two, expect a new release of our data. Once we've managed to clean it up and reparse it and spend all of the computer time that it takes to do that, we'll put up a nice version that hopefully will have slightly less weirdness. It'll still, I promise, have a lot of weirdness in it. But you can play with it. And the big piece of future work is a decentralized version of this project. So what we want to do is we want to detect server impersonation and man-in-the-middle attacks, even if they're not visible from our data center in San Francisco. We want some code that you guys can have in your browsers that will, I guess the ideal case would be actually warn you if you're getting man-in-the-middle with a CA signature. But perhaps even just having some record that it happened at all would be a huge win, even if we can't give you a real-time warning. But we also have this conflicting requirement, which is we don't want to do that by putting some code in your browsers that tells us what websites you're looking at. Over at EFF, we don't want to know what websites you're looking at. We kind of suspect what you're looking at, but we don't want to know about it. So we have this kind of sketch of a design for this. So the idea is this is really a thing that you'll have if you have Tor running, but you're not currently in Tor mode. So you've got a Tor instance there. Perhaps you have Tor button installed in your browser. Not currently in use. We see an SSL certificate coming through to your browser, and we'll fork off in the background. We won't block to slow your browsing down at all. We'll fork off in the background and send it off through Tor anonymously as a submission to the Observatory database. And then perhaps we'll have the opportunity, if we start to have a model of what the attacks here look like, we'll be able to pop up a warning saying, by the way, a minute ago, you got man-in-the-middle by someone. Which is a lot better than, it's not as good as telling you before you enter that password, but at least it's better late than never.
You guess which site. That's right.
And so we have the beginnings of this code, and I guess we'll let you know when it's actually ready. Yeah.
If you guys have any questions, just be
Yeah, me.
Wait a second. People, first, if you leave, take your stuff with you. Okay, thanks. Second, please don't leave. This might be interesting. Questions?
Hi, I was wondering how possible uses of DNSSEC and placing, for example, the public key in the DNS is going to affect the certificate authorities. Are we going to be able to get rid of them?
So we were very optimistic about DNSSEC for a while, and I think there have been things happening in the United States that have made me less optimistic about DNSSEC in the past few months. So I guess you'll get a lot of disagreement. Some people think, let's just use DNSSEC to replace the certificate authorities. I personally think your best hope is to use the two in parallel. So the attacker has to get both a certificate authority signature and the DNS hierarchy to sign off on an attack if the website uses DNSSEC. The problem with DNSSEC, previously I think everyone had been saying, look, these companies that run DNS look like they have a bit of backbone. We aren't seeing much kind of contentious policy being carried out by the root or the .com people. But in the past 3 months, we've actually seen the US government embark on a campaign of censoring websites based on alleged copyright infringement without really proper process through the .com hierarchy. And so actually I'm starting to think maybe we need to look at something other than DNSSEC. We were excited about it, but we don't want a situation where you're exposed to that.
Yeah. You need an honest broker.
Works. First of all, thank you for your fantastic work, and I think that's very useful. Just quickly, the French thing is actually the government authority for information services security. So it's a governmental body. Mm-hmm. We can discuss about it later on. I wanted to know, so you told us that we need to question authority in general. And now that it's so fucked up, what do we do to start over again? Shall we erase the whole database of CAs, and how do we start over again? And as a corollary question, you heard of CA CERT, this volunteer-based authority, certificate authority. What is it worth, and why it is not in Firefox by default yet?
So I think my answer to the question about starting over again is perhaps we do want to start over again. Perhaps not. If we start over again, it's going to be hard to design it right. This is actually a hard problem. And so I think we actually wrote, like, I along with a couple of my colleagues at EFF wrote a white paper about how to do this whole thing differently that we never published, because right as we were working on it, we just convinced ourselves that what we were proposing looked too complicated and too hard to be sure of. And so actually I think the first step to redesigning is to get the data on the current system and to have a clear picture of the problems. And so I think what we hope for from the observatory and then the decentralized observatory is a clear understanding of how many vulnerabilities we're getting through the current system. And then we can design something that may be a complete redesign or a cross-check for the existing system based on the actual problems that are occurring.
Also, the system isn't useless as it is right now. For a lot of threats, actually, it's not just better than nothing, but it's actually pretty useful, right? I definitely am using HTTPS for my traffic here on the wireless network, right? And I haven't had a lot of trouble with that. So, you know, there's a lot of benefit, even if the thing isn't firm enough for us to trust completely and needs huge improvements. Having insight into that, by the way, is an absolutely key part of making it better.
Hi. Hello. The SSL or TLS allows
for has an option for OpenPGP keys as well as X509. As you said, you don't really like X509 certificates. So, first question is, did you detect any of those, or did you have code for it?
We didn't have code for it. So if the answer that the server gave contained something that wasn't encoded in the PEM file formats that you expect for a...
No, it would though with that spec. We probably have those keys in the database. We haven't done any analysis of them. If we do, that'd be a great query to write.
And whether or not our parser imported them correctly, we have the raw results file. So we have one download that's just the raw server responses.
Yeah, and I believe I've seen some of those actually in the all certs tables. They're just never in the valid certs because they don't come up under any of the browsers. Also, PGP, kind of a complicated thing, right? One of the great things about web browsers is they work for normal people that don't actually know like the details of how their Ethernet controllers VLSI circuits work. That's
less centralized. PGP.
Right. The other structural problem, and this is a kind of damned if you do, damned if you don't. Suppose we're convinced that PGP, or something else, something, let's call it, future encryption, is a better model than X509. The problem is, until you've switched everyone over to your alternative verification mechanism, every client that's widely used needs to understand both X509 and PGP and future encryption, and so you just get a larger and larger attack surface. So it's kind of, although X509 is terrible, we may be doomed to live with it kind of forever, or for as long as the web and other SSL-based protocols are around, because until your clients can throw it away, you're still going to have to parse it.
So we have an online question, which is, did you find any duplicate certificate IDs from the same CA?
Oh, like duplicate serial numbers from the same CA. That's a good question.
I didn't run that. I don't think
that's
we ran
a really
that
good query. I'm going to run that right when I'm not standing in front of an audience. Sorry, don't have that answer.
We could run it in front of the audience.
You've got your.
At least publish the result on the talks.
Yeah.
So,
you want to?
Yeah, sure.
All right.
Yeah.
All right. He's going to do it. Fire off the next one if you got.
So, if you have any more questions, please just come forward and let's do it in a smaller setting. And when you leave the room, please leave on the back, because we're trying something new and having people wait on the front and just rotating the audiences. Let's see how this works out. Thank you.
Thanks.